In the winter of 1841, a carpenter named Eli Caulfield nearly froze to death inside a cabin he had built with his own hands. He was burning 12 cords of wood a season and still waking up to frost on the inside of his walls. It wasn't bad luck, it was bad physics, and he didn't yet know the difference. What followed was one of the more quietly remarkable feats of practical problem-solving on the early frontier. A man who understood joinery and timber, but knew nothing about heat transfer, teaching himself, through hard experience and outside knowledge, how to build a shelter that actually worked. His story spread across the Colorado Territory and beyond, not because he wrote it down, but because the results were undeniable. People came in from the cold, felt the difference, and wanted to understand why. Eli had done everything the conventional way. He chose a sheltered site in the South Fork Valley with good southern exposure and creek water nearby. He felled his logs in August, stacked them fast, chinked the gaps with creek clay and dried moss, and positioned his fireplace flush against the north wall, exactly where every other man in the Colorado Territory put his. This wasn't carelessness. It was the received wisdom of the frontier, passed from builder to builder, without anyone stopping to examine whether it actually made sense. He moved in before the first October freeze, confident in his work. By December, he understood he had made a serious mistake. The clay chinking cracked in the first hard freeze and crumbled out in chunks. The dried moss fell away with it. Gaps opened in the walls that let in enough wind to make the fire sputter and lean sideways. On the coldest nights, ice formed on the inside of the walls, not the outside, the inside, even with a full roaring fire burning wood as fast as he could split it. He burned 3 cords in January alone, 3 more in February, and by spring thaw he had consumed more firewood than a family of 4 would need across 2 full winters. Summer brought a different and equally miserable problem. The same thick log walls that failed to hold heat in winter trapped every drop of it in July. The cabin became an oven. Eli started sleeping outside on the ground in August because the air inside was hotter than the air outside, a shelter that worked against him in every season. The fundamental problem was one that most frontier builders never paused to consider. Building a cabin was understood as a matter of craftsmanship. Choose good timber, work the joints tight, chink the gaps, build a big fire. What nobody discussed was how heat actually behaves, how it moves, what stops it, what stores it, and what wastes it. Eli knew he had made mistakes. He just didn't yet have the framework to identify what they were. The answer came from 2 unlikely sources that fall, both of whom arrived in the South Fork Valley by chance and left Eli with ideas that would reshape how he thought about shelter. The first was an elderly Finnish trapper named Antti Salo, who had been working the southern Rockies since the 1820s. He came through the valley trading elk hides. In the autumn of 1841, looked over the cabin and began explaining what he saw in the patient way of a man who had watched too many younger men make the same mistakes. Heat, Antti explained, is not simply a quality of air that can be captured by enclosing space. It behaves according to specific physical principles. It radiates outward from hot surfaces, it conducts through solid materials at different rates, and it rises. Every single one of those behaviors was working against Eli's cabin. The fireplace against the outer north wall was pouring half its radiant heat directly into that wall and conducting it outside. The log walls themselves conducted warmth away steadily, day and night. Hot air leaked out through poorly sealed gaps near the roofline, and the cabin had no internal mass, nothing capable of absorbing and holding warmth after the fire died. The moment Eli let the fire drop to coals, the heat was gone within an hour. If you've enjoyed this video so far, it would mean the world to us if you subscribe. We're a small channel, and every single subscriber helps us grow and keep creating more content for you. Thank you so much for your support. We truly appreciate it. In Finland, Antti explained, builders had worked through these problems over centuries of brutal winters. The fireplace went in the center of the house, so that its radiant heat escaped into the living space on all sides rather than half into the walls. More importantly, the fireplace was built enormous, not for the firebox itself, which could be relatively modest, but for the stone mass surrounding it. A massive stone structure would absorb heat slowly during a long evening fire, then release that stored warmth gradually through the night. One long hot burn in the evening could keep a cabin livable until morning without another log added. The stone was doing the work that Eli had been trying to do with an endless supply of firewood. The second source of knowledge arrived later that same autumn. Stan's-at-Water was a Ute woman, wife of a Mexican trader named Corrales, who was camped near the valley. She observed Eli working on his cabin and offered a principle he carried for the rest of his life. A single wall, no matter how thick, puts interior air in direct thermal contact with exterior cold through one continuous material. Heat moves through it steadily toward the cold side. Add a second wall with a gap of still air between them, and the equation changes. Air is a poor conductor when it is not moving, and a trapped still air gap between two walls dramatically slows the transfer of warmth outward. Two walls with a gap between them outperform a single wall twice as thick by a significant margin. She also described building partially into the earth to use the ground's stable temperature as passive insulation, designing high openings to allow rising hot air to escape in summer, and orienting shelters to capture the low winter sun while blocking the high summer sun with roof overhangs. Eli spent the next 3 months thinking through all of it. He was a carpenter. He understood materials and structure. What he had lacked was a framework for understanding why those materials behaved the way they did in relation to temperature. Now he had one. He began cutting timber that November when the sap was down and the wood would season properly. He let the logs sit through the entire winter, stacked with air spacers between each one. By the following May, he had dry, dimensionally stable timber, not the green, sap-heavy logs he had used the first time, which had shrunk as they dried and opened fresh gaps every spring, no matter how carefully he rechinked them. Dry timber was the foundation of everything else. Rather than building directly on the earth, Eli set stone piers at the corners and midpoints, raising the entire floor structure 2 feet off the ground. This served 3 purposes simultaneously. It kept the bottom logs completely dry, eliminating the ground moisture that would wick into the wood and accelerate rot. It created a buffer of still air between the frozen earth and the floor above, and it provided a cool, protected storage space beneath the cabin for food and supplies. The floor itself was built from split log puncheons, logs halved lengthwise and laid flat side up across heavy crossbeams. Wood conducts heat far more poorly than bare earth, meaning far less warmth was lost downward. The still air gap in the crawl space below added another layer of thermal resistance, and on the coldest mornings the difference underfoot was immediately obvious to anyone who crossed the threshold. The north and west walls, the faces that bore the hardest winter wind, went up in 2 layers. Eli used large, carefully debarked logs for the outer wall, hewn flat on their contact faces with a draw knife and adze. Flat faces meant tighter contact between logs, fewer voids, and less chinking overall. The inner wall was set 2 feet inside the outer wall and built from smaller diameter logs, also hewn flat. Between the 2 walls, Eli packed the gap in deliberate layers. Dry moss first along the bottom, then crumbled bark and forest duff, then another layer of moss, then a clay and grass cap to seal the top against moisture. Each material was chosen for its ability to trap still air. The moss and duff were full of tiny air pockets that conducted heat poorly. Even if moisture found its way into the outer edge of the gap, it would pass through multiple material changes before reaching the inner wall. The south and east walls received single-wall construction, but chinked with a far better compound than Eli had used before. Split wood wedges were hammered into each gap first, giving the chinking something solid to grip. Over those went a paste of clay, coarse sand, and cattle hair, traded from a rancher down the valley. The hair acted as fiber reinforcement, preventing the surface cracking that plagued standard chinking through freeze-thaw cycles. Wood ash added later reacted with moisture to slowly harden the compound over time. 2 coats went on, the second applied, while the first was still slightly damp, so the layers bonded together, and the result held through multiple winters without cracking loose. This was the most radical departure from convention, and the one that drew the most skepticism from every passing trapper who came through the South Fork and saw the construction underway. Eli built the fireplace not against any wall, but positioned in the interior of the cabin, roughly centered on the long axis and set about 4 feet back from the north wall. The firebox was practical, sized for decent-length logs with a proper fireback angle to reflect heat forward, but everything surrounding it was built far larger than the firebox strictly required. The hearth extended several feet out from the firebox in all directions, large flat stones set level on a bed of packed clay. The chimney was thick-walled, built from the densest riverstone Eli could haul, mortared with clay and fine sand. Stone benches extended outward from both sides of the fireplace base, knee-height, about 2 feet deep, serving simultaneously as seating, gear-drying platforms, and additional thermal mass. The finished structure weighed somewhere between 3 and 4 tons, all of it inside the insulated envelope of the walls, where its stored heat had nowhere to go except into the living space. A fireplace against an exterior wall radiates heat in all directions, meaning roughly half escapes into the wall and out of the building. A fireplace in the interior radiates entirely into the living space, and a large mass of stone absorbs surplus heat from a hot fire and holds it for hours after the flame is gone, releasing it slowly into the surrounding air rather than allowing the warmth to spike during the fire and crash the moment it dies. Eli's routine became this: build a hard fire in the late afternoon, hot enough that the stone was uncomfortable to touch after 2 hours. Let it burn down. Bank the coals around 10 or 11 at night. Sleep. Wake at dawn to a cabin that had cooled, but slowly. The stone still faintly warm to the touch, the interior having dropped perhaps 15 degrees over 8 hours rather than crashing toward outside temperatures within 90 minutes as his first cabin had done every night. About 5 feet above the firebox, he built a slight offset in the chimney. Not enough to restrict draw, but enough to force the rising smoke column to interact with a larger stone surface before exiting, extracting more heat from the exhaust before it left the building. A stone damper near the top of the chimney, operated with a long iron rod, could be partially closed once the fire was low, reducing the warm air escaping up the flue while still allowing smoke to vent safely. Standard trapper cabin roofs were low-pitched, built fast and covered with whatever was at hand. They leaked, let cold in, and sagged under accumulating snow loads. Eli built a steeper pitch. It shed snow rather than letting it pile into dangerous weight, created a larger airspace between the ceiling and the roof boards, another dead air insulating layer, and gave him the vertical room to add something he had observed on prairie sod houses. He laid split cedar shakes as the base layer, fitted tight and pegged down. Over those went a troweled layer of clay, about an inch thick, worked into every gap as a moisture barrier. Over the clay went 4 inches of packed soil contained by wooden edging boards at the eaves. By midsummer, grasses and wild flowers had rooted into it on their own. The sod layer performed differently in each season, and usefully so in both. In winter, the soil and root mass insulated the roof, the way earth insulates a cellar. Deep soil temperature changes slowly, creating a stable thermal buffer above the ceiling. In summer, the sod absorbed incoming solar radiation directly, warming the soil rather than the cabin interior, while the plant's moisture release further cooled the roof surface. The living roof made the cabin measurably cooler in July than any shake-only roof Eli had ever been inside. 2 small openings near the roof peak on the east and west gable ends, fitted with tight wooden plugs in winter, became ventilation ports in summer. Hot air rises and collects at ceiling level. Opening these ports allowed that accumulated heat to escape, drawing cooler air in from below through gaps at the lower level. A simple convective loop with no mechanical parts, no maintenance, and reliable seasonal performance every year. The first serious test came in November of 1842, when a cold snap dropped temperatures to 20 below for 4 consecutive days. Eli fired the fireplace hard in the afternoon. By evening, the stone was radiating heat you could feel from 6 feet away. He banked the coals around midnight and went to sleep without his heavy coat on. The first time that had ever happened in a mountain cabin. He woke at dawn to mist from his breath, but the stone was still faintly warm to the touch. The temperature had dropped gradually, 15 degrees over 8 hours, not 40 degrees in 90 minutes. He burned roughly 1.5 cords that month. His first winter in the valley, he had burned 4. Word moved the way it always did in those communities, slowly through personal visits and chance encounters at trading posts and seasonal camps. Other trappers and settlers came through the South Fork, sat in the warmth of Eli's cabin, and wanted to understand what they were experiencing. Many were skeptical. The double walls seemed like unnecessary labor. The interior fireplace looked wrong to men accustomed to building fireplaces against outer walls. The sod roof drew jokes about things growing on a man's house. Most of them came back the following winter asking how to build one. A trapper named Devereaux adapted the design for a smaller one-room structure, using double walls only on the north side while still capturing meaningful benefit. 2 brothers from Tennessee built their central fireplace so massive it reportedly stayed warm for 30 hours after the last fire. An old-timer near the pass added only the sod roof to his existing cabin and called it the single best improvement he had ever made. Each person adapted the principles to their materials, their skills, their available time. That flexibility was part of the point. Eli never insisted on exact specifications because the specifications mattered far less than the underlying logic. Trap still air in the walls, store heat in dense mass inside the insulated envelope, seal gaps against drafts, use the geometry of the sun to your advantage. Understand why something works, and you can make it work with whatever you have available. The techniques spread gradually across the decade, into Montana territory, along the emigrant trails, into the homestead settlements that replaced the trapping economy as the 1850s arrived. Eli Caulfield stayed in the South Fork Valley until 1858, guiding emigrants and running a small trade post, answering the same questions about his cabin season after season. He never framed it as an invention. He had been cold, found people who understood why, and applied what they shared as carefully as he could. A Finnish trapper carrying centuries of northern knowledge, and a Ute woman who had grown up understanding shelter in ways most frontier builders never considered. Between them, they handed Eli the framework. He built from it, tested it, and shared it with everyone who came asking. The cabin he built stood for over 30 years after he left the South Fork. The stone fireplace outlasted everything else, still standing when government surveyors came through in the 1890s and puzzled over who had built such an enormous hearth in the middle of a room, so far from every wall. They didn't know, but it worked exactly as it was meant to, which in the end was the whole point.